Hello all, in this video we will learn about the structure of wireless communication link. The goal of a wireless link is the transmission of information from an analog source such as microphone, video camera via an analog wireless propagation channel to an analog information sink, that means a receiver like loudspeaker, TV screen. So digitizing of information is done only in order to increase the reliability of the link. Any structure of wireless communication link may have a transmitter and a receiver. So the transmitter can add redundancy in the form of a forward error correction code in order to make it more resistant to errors introduced by the wireless communication channel. The encoded data are then used as input to a modulator which maps the data to output waveforms that can be transmitted. So by transmitting these symbols on specific frequencies or at specific times, different users can be distinguished. So the signal is then sent through the propagation channel which attenuates and distorts it and adds noise. So at the receiver part, the signal is received by one or more antennas. So the different users are separated, and if the channel is delayed dispersive, then an equalizer can be used to reverse that dispersion and eliminate intersimple interference. Afterwards, the signal is demodulated and the channel decoder eliminates the errors that are present in the resulting bit stream. A source decoder in the receiver finally maps these bit streams to an analog information stream that goes to the information sink such as loudspeaker or TV monitor. So in the case when the information was originally digital, this is the last stage which is omitted. Now let us see the block diagram of a radio link with digital transmitter and analog propagation channel. So here the very first block is the information source. Information source provides an analog source signal and feeds it into the source ADC, that is analog to digital converter. This analog to digital converter first band limits the signal from the analog information source and then converts the signal into a stream of digital data at a certain sampling rate and resolution. Then we have a source coder block which uses a priori information on the properties of the source data in order to reduce redundancy in the source signal. Then we do have a channel coder block which adds redundancy in order to protect the data against transmission errors. We have a signaling stage where it adds the control information for the establishing and ending of connections, for associating information with correct users and synchronization, etc. We do have a multiplexer block in the transmitter side which can be used to combine the user data and signaling information, and this combined data from the multiple user is being sent over the channel with the help of this multiplexing process done. Then we have a baseband modulator which assigns the gross data bits to complex transmit symbols in the baseband. So spectral properties, intersimple interference, peak to average ratio and other properties of the transmit signal are determined by this step. Then we do have oversampling and quantization which determine the aliasing and quantization noise. So the transmitter side digital to analog converter. We do have a digital to analog converter at the transmitter side which generates a pair of analog discrete amplitude voltages corresponding to the real and imaginary part of the transmit symbols. The analog low pass filter in the transmitter eliminates the spectral components outside the desired transmission bandwidth. These components are created by the out-of-band emission of an ideal baseband modulator. The transmitter side local oscillator provides an unmodulated sinusoidal signal corresponding to one of the admissible center frequencies of the considered system. The upconverter stage is used to convert the analog filtered baseband signal to a passband signal by mixing it with the local oscillator signal. The RF transmit filter eliminates out-of-band emissions in the RF domain. Even if the low-pass filter succeeded in eliminating all out-of-band emissions, upconversions can lead to the creation of additional out-of-band components. In this block diagram, we can even see the analog propagation channel which attenuates the signal and leads to delay and frequency dispersion. Furthermore, the environment adds noise such as AWGN, additive white Gaussian noise, and co-channel interference with the original signal which is propagating in the space. So in this diagram, we see the digital receiver chain for mobile communications and multiplexing. So the analog low pass filter in the transmitter, we have already seen that it eliminates the spectral components outside the desired transmission bandwidth. In the receiver side, when we are the first thing that we're going to see is actually called as a receive filter, which performs a rough selection of the received band. So the bandwidth of the filter corresponds to the total bandwidth assigned to a specific service and can thus cover multiple communications channels belonging to the same service. And then we have a low noise amplifier, which is shortly called as LNA, which amplifies the signal so that the noise added by the later components of the receiver chain has less effect on the signal to noise ratio. The receiver local oscillator provides sinusoidal signals corresponding to possible signals at the transmitter local oscillator. So the frequency of the local oscillator can be fine-tuned by carrier recovery algorithm to make sure the local oscillators at the transmitter and receiver produce oscillations with the same frequency and phase. The receiver down converter converts the received signal into baseband. The receiver low pass filter provides a selection of desired frequency bands for one specific user. The automatic gain control in the receiver amplifies the signal such that its level is well adjusted to quantization at the subsequent ADC, that is analog to digital converter. And the receiver ADC converts the analog signal into values that are discrete in time and amplitude. Carrier recovery stage determines the frequency and phase of the carrier of the received signal and uses it to adjust the receiver local oscillator. The baseband demodulator in the receiver stage obtains the soft decision data from the digitized baseband data and hands them over to the decoder. So the baseband demodulator can be an optimum coherent demodulator or a simpler differential or incoherent demodulator. If there are multiple antennas, then the receiver either selects the signal from one of them for further processing or the signals from all of the antennas have to be processed. Simple timing recovery uses demodulated data to determine an estimate of duration of symbols and use it to fine-tune sampling intervals. The decoder in the receiver uses soft estimates from the demodulator to find the original source data. In most cases, uncoded system, the decoder is just a hard decision device. For convolutional codes, maximum likelihood sequence estimators are used. Signaling recovery in the receiver identifies the part of the data that represents signaling information and controls the subsequent demultiplexer stage. The demultiplexer stage separates the user data and signaling information and reverses possible time compression of the transmitter multiplexer. The source decoder is the final stage of the receiver where it reconstructs the source signal from the rules of source coding. So if the source data are digital, the output signal is transferred to the data sink. Otherwise, the data are transferred to the digital to analog converter, which converts the transmitted information into an analog signal and hands it over to the information sink.